We are now.
Okay, so it's time to resume our seminar with today Tilmann Wurzbacher from Institut Élie Cartan de Lorraine, here with us to introduce us to the world of two-plectic manifolds, prequantization or quantization, starting with non-degenerate three forms rather than two forms. And in this context, the appearance of categorified geometric objects, groupoids, gerbes, and whatnot. Tilmann, the floor is yours. We're happy to have you here.
Thank you very much. First of all, to Kasia. I'm very happy and honored to speak in this online seminar. I would have preferred to come to Warsaw, but on the other hand, it's very comfortable this way. And well, at least I chose Warsaw as a background in LaTeX Beamer. So, okay. I want to speak about, well, the subject is there. This is part of a PhD thesis of Gabriel Silvestre with me. And I'm coming back to the subject because, of course, you see the word pre, and of course, one hopes to go not to prequantization, but to have something like quantization. And that's why, which rekindled my interest in the subject. I chose a long format because I want to motivate it. I want to explain some notions and then give the results. There are, in the end, some technical formulas which I cannot prove in the talk. It's in the paper, which I will quote, and I will be happy to discuss this eventually by email if you have questions. But I prefer to give more the ideas than, of course, I give the formulas, but more the ideas behind. I cannot prove everything. Okay, so let's start. Something is not working.
We can see your slides and we can see your pointer.
Yeah, I want to do this going step by step, but it doesn't work. Okay, this is a list of contents. I don't need it for now. Okay, this is a motivation. I remind what is the typical setup of a Lagrangian field theory. So you have fields, which are maps or sections, and you have a Lagrangian, and this yields an Euler-Lagrange equation, which I call star, which I don't write down here. And then there are typical ways to quantize it, either via path integrals, which are defined in some cases, so essentially in the free case, so it's not covering interactions, but by usual Feynman techniques, you can try to extend it. Even if as an integral it's not defined, it might be defined on a combinatorial level. And another approach you find in physics books is you go from a Lagrangian description via a formal Legendre transformation to a Hamiltonian description, but in infinite dimension on the cotangent bundle of this mapping space. And then you have the components of the fields, and you impose on the classical level canonical brackets, and canonical quantization means you just formally impose the operator commutators, which are the sort of quantum version of the classical bracket, but this is rather formal, and it goes to via T star of a mapping manifold, which is not even fresh a manifold, so functional analysis is getting subtle. And that's the reason why after several years I spent on infinite dimensional manifolds, I fell in love with multisymplectic geometry because it tries to formulate field theory, classical field theories in finite dimensional terms. So the traditional setup is you have a fiber bundle E, might be trivial in the first case, over a base sigma, which is n-dimensional. It's not only time, it's n-dimensional. And then you have sort of a multi-cotangent, restricted multi-cotangent bundle over it, lambda n2, which I described there. So these are not, it's not the cotangent bundle, it's a higher power, depending on the dimension of the base manifold. So the fields are defined on an n-dimensional object. So you use n forms, and you don't use all of them. You take only a restricted set of n forms, and I wrote it down. If you have two or more vertical vector tangent vectors, the form will be annihilated. This can be calculated, and it was done, I think, maybe in the 70s in Poland, in the 90s again in Spain. This is sort of a twisted affine dual of a jet bundle, and so it's not so far from the Lagrangian description. In fact, there is also a sort of Legendre transformation between them. But my point of view is that nowadays, if you do symplectic geometry, you don't have to justify yourself by saying the cotangent bundle is dual to the tangent bundle. Yeah? And the same point of view I have with multisymplectic geometry. I do not justify multisymplectic geometry via Legendre transformation. I think it's just a subject in itself. It's a Hamiltonian way to formulate field theories. It might or might not be completely equivalent to Lagrangian description, but I'm interested in this Hamiltonian case. Okay, if you want to write down dynamics, then you start as in symplectic geometry, but one has to take care. I take a function, and then dh is a one form, but omega is an n plus one form. So if I contract with something which is the unknown is an n vector field, a multi-vector field of degree n. And so this is not really a map, it's not a field, it's not like a flow, because there's a kernel and so on. So you need an extra step to really solve, and this is you have to look for a section psi of this bundle m of pi, which I described over sigma, and you look at sections which fulfill sort of the dynamical version of the equation we had here. This is the equation. You contract the multi-vector field in omega and you get dh. And now you contract, in fact, the following thing.
Excuse me. What was m of pi? Was it this wedge 2 n?
Yes, this is a lambda n2. This is a restricted multi-cotangent bundle. It's a sub-vector bundle of the n forms. The base is n-dimensional. I work with n forms, but I don't work with all of them. I have this condition that if I put in two vertical tangent vectors, it's already zero.
Thank you.
This I call m of p, just to have a notation. Okay, so the dynamical formulation is I look at sections on this n-dimensional base, so something like fields on an n-dimensional base. And for me, it's natural to assume that sigma is orientable or even oriented, and even I supply a volume form. Then I have also a co-volume. This is just dual to the volume form. And so one can push forward the co-volume. So point by point, this is an n form, n vector field. I contract it in omega, and this should give minus dh or dh. So this is like the Hamilton equation. in the one-dimensional case, it's easier because once you have this non-dynamical equation, just a contraction equation, by unicity of existence of flows, then everything is done and you have all your section and so on. But this is not true if you have a higher dimensional base. Okay.
May I ask a stupid question? So, if I understand correctly, you took your base bundle E to be trivial, right? It was something.
Yeah, it's not necessary. It's just no. In general, of course, it's not trivial. It's just for an easy description.
So it's not essential. Okay, thank you.
No, in general, it's not trivial, and it's not a vector bundle in general. Okay, don't think it's a vector bundle. It's just a fiber bundle. Okay.
Fiber. Okay.
Okay. Star was the Lagrangian formulation. Double star is this, and in good cases, if the Legendre transformation is a diffeomorphism or local diffeomorphism, so in the regular and hyperregular cases in the classical language of mechanics, these equations are equivalent. Okay, one can also have the fun of writing it down in local coordinates. Then you
There
get
were two different H's. Can you elaborate on this?
Yes. The round H is a function which is not on the M of pi, but on this space, this quotient, which has one coordinate less. This sometimes in the literature is called P of pi. And this is the analog of time-dependent mechanics if you work on interval times T star of Q. Okay? But you can also formally go to T star of the interval times T star of Q. This is symplectic. And if you have your Hamiltonian function, a time-dependent Hamiltonian function, which is defined on interval times T star Q, then you can go formally up to T star of the interval times T star Q. You add up a variable, which is often called E, but here the letter E is done. This is the energy which you add up. And if you write down the Hamiltonian equations on this bigger space, you get one redundant equation. And the right way to write the Hamiltonian upstairs is to write it as the Hamiltonian which depends on time, calligraphic H, minus the energy, or plus. This depends on sign rules. Okay. So this is a typical analog of a time-dependent Hamiltonian, but you want to get rid of it and you want to work on a symplectic manifold. So you add the coordinate which is conjugate to time, which is energy, which are called small p. But of course, you can generalize and take an arbitrary H. It's just to make contact with the classical case. That's okay?
Yep, thank you.
And if you are in this classical case, the analog of time-dependent mechanics, then you have what is called the Hamilton-Volterra equations, which look a little bit like Hamilton equation, but you have this nasty sum there, which gives you PDEs, which are not elliptic, not parabolic, not hyperbolic in general. So there are quite interesting PDEs showing up, and I asked a couple of people from PDEs. They have no idea how to solve them. Okay, but case by case, certain of them you can solve geometrically.
Tilmann, may I ask you something connected to the previous transparency? So this, you mentioned this Arnold-like trick of adding the time variable and so on. So
Yes.
this, I guess, this generalizes to the contact case. So in the case of classical mechanics, this is one way to approach the formulation of contact Hamiltonian mechanics.
Yeah,
Have you tried to do it in this multi-symplectic framework?
Well, I guess what I do there, I never checked it in detail. I guess this is a transition from multi-contact to contact to multi-symplectic.
There's some reference where people did it in detail? this
Well,
construction?
I guess there are recent papers of the Spanish school on multi-contact, and you start with Roman Roy or Manuel de Leon and check on the archive. I think
Okay,
they are interested in multi-contact quite a lot now.
okay, thank you.
For me, this is in a certain sense motivation because I'm more interested in the general multi-symplectic setup.
Mhm.
Okay, these are these Hamilton-Volterra equations. So I'm citing Roman Roy there and myself with a small paper with a PhD students where we study this in a bit of detail. But it's essentially well known. Okay, since many years. So how to quantize in the case n equal 1, there is geometric quantization in the Kostant and Souriau sense, and of course deformation quantization, which in some cases are close to each other, in some cases maybe not. I will come back to this a little bit. And in the case n bigger than 1, not so much is known. There are some tentatives, but I think quantization is not so much done. And I try the two-plectic cases, at least for two reasons. One is this is the first case, which is really beyond symplectic, so it's natural to start there. And the second case is I'm, even though somebody claimed it in the beginning, this is in a certain sense categorified higher geometry, but I approach it in a very traditional way, in a very differential geometric way. So I try to write down, for example, all arrows. So, and if you go higher up than 2, probably you cannot write down the arrows, or it's getting very, very difficult to read, to understand. So n equal 2 in a certain sense is an easy case. It's like higher categories and two categories. Two categories, you can write down the arrows. General higher categories, maybe you need another way to organize yourself in a more categorical sense way. Okay. Another reason is that there are really many multi-symplectic manifolds of degree 2, two-plectic manifolds. So let's have a look at the general definition. A multi-symplectic manifold is a manifold with a n+1 form, which is closed and which is non-degenerate in a natural sense. It means if you make a contraction with a tangent vector, then you have a map. This contraction map goes from the tangent bundle to the nth power of the cotangent bundle. And if you calculate the ranks of both sides, there's no hope that this is an isomorphism as in symplectic geometry. So you can hope that it is injective. Okay. And that's the definition for n-plectic manifold. Quite some work nowadays also on what is called pre-multisymplectic. So you just simply take a closed n+1 form. Okay. And certain constructions work there. What one should be aware of the following problem: if you plug in not a tangent vector, but a bi vector, so V wedge W or something like this, then it's not injective. Yeah? I think the Spanish school, they speak of one non-degenerate, two non-degenerate, and so on. And typically, even the simplest examples, as this M of pi, which I discussed, is already not two non-degenerate. The only case where everything works fine is if you take an n+1 dimensional manifold with a volume form. Then it's non-degenerate on all levels. But this is rather the exception. It's even true in the symplectic case. If you plug in an arbitrary wedge of two tangent vectors in the symplectic form, it will not be non-zero. No. Okay, so a one-plectic is symplectic, okay? Now I give a bit of a zoo. So first case is what I said, this restricted multi-cotangent bundle over a two-dimensional sigma. Then you take a three manifold with a volume. It's also two-plectic. Then you have this example class which goes back to Souriau. He takes products of a symplectic manifold with a one-dimensional manifold, and he takes the wedge of the symplectic form and the volume form on the one-dimensional manifold. This is also a three form. This is almost multi-symplectic, which is rather close to symplectic. Then you have a different class, which I call real Calabi-Yau. You take a six-dimensional real manifold with an almost complex structure. In good cases, it's a complex structure, so it's integrable. And you take a closed complex volume form. So if the complex structure, almost complex structure is integrable, then a complex volume form is automatically closed. And you take the real part of this holomorph, this complex volume. This is also two-plectic. Then there is a well-known example. You take a semi-simple Lie group. In fact, it can be a little bit more general, but I don't want to give the most general version. You take a semi-simple Lie group, for example, a compact, but it's not necessary. And you have the so-called Cartan form. So you take the killing form, B, and you construct a three form in the neutral element by plugging in three elements of the Lie algebra, the tangent space in the neutral element. And you do it in the following way. You take the killing form of the first vector together with the commutator of the second and the third. This is non-degenerate because it's semi-simple, so the derived algebra is the algebra. And it's closed because you take, this is ad invariant, and then you push it from the left. It's automatically also invariant from the right. And the bi-invariant form is always closed. So it's a closed three form, which is non-degenerate because you check it in the neutral point. This is an interesting example from the point of view of coordinates, because you don't have the analog of Darboux coordinates in this case. So it's rather well described in an algebraic sense, but in local coordinates, you cannot standardize it in standard coordinates. Another class is what one calls manifolds with closed G2 structure. So it's seven-dimensional manifolds with a closed three form, which you can describe like this. Okay, this is a rather pedestrian way to describe it. One should describe it in terms of holonomies, in terms of G structures, but I don't want to make it too long here, and it's not the point of the talk. So this is a G2 manifold. And a related case is the following thing. On R7, there is a standard G2 structure, which is given by this form omega tilde. Omega tilde of three vectors is the vector product of two vectors, and then you take the scalar product with the third vector. So this is not the vector product in R3, it's a vector product in R7. It relates to the questions which division algebras you have over R. So you have the quaternions and the octonions, and the quaternions are of dimension 4. You take the imaginary quaternions is R3, and the octonions is R8, and you take the imaginary octonions is R7, and both have a vector product. And this form you can pull back to S6, and it's still, of course, it's closed, and it's still non-degenerate. And this is also a rather surprising object because it's a 3 form defining a two-plectic geometry on S6, but it has a potential. So it's rather different from symplectic geometry. You have a compact manifold with a two-plectic structure, but the two-plectic structure has a potential. There is no trick with volume forms which prevents you that the cohomology class of omega is 0. It can be 0. Okay, now I will recall what was geometric prequantization in the classical case. So it goes back to Kirillov, Kostant, and Souriau. I think the first time you have something like this is in a paper of Souriau in Communications in Mathematical Physics in the first volume, the first issue of Communication in Mathematical Physics. There's an article of Souriau, and I think this is in a certain sense more general, and it's before the habilitation of Kirillov. It's more general in the sense I think he's not restricted to coadjoint orbits. Okay, the theorem says if you have this is sort of more or less a differential topological theorem. It's not really symplectic. If you have a closed integral form, so this means that the cohomology class of omega is integral. So either you say it's in the image of the Z, singular Z cohomology inside the RAM, or you say you take a closed 2-cycle, you integrate, and you get an integer. On a finite dimensional manifold or on an infinite dimensional manifold, if you have smooth partitions of unities, so this can happen. I'm not interested in this. Well, okay, I'm interested in it, but so you need something like smooth partition of unities to do it also in infinite dimensions. Okay, you have this form. Then there exists a smooth principal S1 bundle, P over M with a connection form. In the naive sense, it's really a one form with values in the Lie algebra of S1. So it's in I times R. It's I times a one form. And it defines the splitting of the tangent spaces in the vertical space, which is just the action of S1, and the horizontal space isomorphic to the tangent space of the base manifold. And this form A has a curvature FA, or in this case, it's in the Abelian gauge theory, so it's just dA. And you can normalize it such that it's minus I times 2 pi, the pullback of the form omega to the total space. And this implies that the Chern class is the class of omega. But there is a small remark to make. This is not the Chern class. This is a rationalized Chern class because you don't see any torsion. You see only the rational part of the cohomology because you started with a form. Okay, that's this remark. So neither the total space P nor A are unique. Okay, obviously A is not unique. You add why a gauge transformation here does not change the first term, and then you have a second term, but this goes away if you take curvature. And P is not unique because you can tensorize P by a torsion bundle, by a S1 bundle, such that a certain power of the bundle is trivializable. So this is exactly the point with this rationalized Chern class, because you don't see the torsion. And the second theorem in this context of Kostant, Souriau, the second theorem is if omega is non-degenerate, if omega is symplectic, then here I concentrate on finite dimensional manifolds, because otherwise you have discussions on what is a vector field. Is a vector field a derivation or a section of the tangent bundle and so on? And I don't want to discuss this now. So I take a finite dimensional manifold with an integral symplectic form. Then I have a principal bundle P and a connection A, as in theorem 1. And then there is a prequantization map. And the prequantization map goes from what is called classical observables, which are the C-infinity functions on the manifold. Of course, this can be discussed. I mean, maybe measures would be a better way to define an observable, but the traditional point of view is functions with the Poisson bracket induced from the symplectic form. And you have a map which goes to the symmetries of P with A, which is simply the set of vector fields on the total space P, such that the flow preserves the connection form LXA equals 0. And this is this well-known formula of, well, I learned it from Kostant, from the long article of Kostant on prequantization in the 1970 lecture notes volume Analysis 3, edited, I think, by Attia. You take F, you take the Hamiltonian vector field associated to F on the base manifold XF, and you take the horizontal lift of XF to the total space. Because you have a connection A, you can take the lift. And you add a certain rotation. Zeta is simply the Euler field or the rotation field. This is the right action of S1. And you decorate this Euler field by a velocity factor, which is just the pullback of this function. So this means on each fiber of P, you fix the angular velocity, because it's q upper star of F on a fiber is constant. But going from one fiber to another, the angular velocity will vary. So, and this sum is a symmetry of A. And in fact, this is not only a map to the symmetries, this is a Lie algebra isomorphism. The symmetries simply are Lie algebra by taking the commutator of vector fields, and the C-infinity functions are a Lie algebra by the Poisson bracket, and this is a Lie algebra isomorphism. So I get all symmetries of the principal bundle with the connection. So this is a rather complete answer in a certain sense, at least on a classical or on a semi-classical level. You get all the interesting symmetries by the Poisson algebra of functions. Okay, this is the second theorem here. And this will be more subtle when we come to the two-plectic case.
Why does this vector field annihilate A?
Which one?
X tilde F plus Q star F times Xi. Why does it satisfy LXA 0?
Well, the first part is well, the easiest way is to calculate maybe with the Cartan formula. Lx is d iota x plus iota xd. So if you plug in xf tilde in A, it's 0, okay, because it's a horizontal lift. On the other hand, if you take dA, then it's essentially the symplectic form, and xf is a symplectic vector field on the base. So the first part is okay. And the second part, the one form is on a general principal bundle, it's ad equivariant, but here it's a Abelian group. This means the one form is invariant. So L of zeta of A is 0. So this is the second part is also 0. That's okay or it's not clear?
More or less clear, yeah. I'm not sure.
Okay. Okay, some remarks. I already said that the classical observables are the C-infinity functions. Well, very often prequantization is not formulated in terms of the principal bundle P, but in terms of a complex line bundle L. And the transition is simple. I take P, I represent S1 on C in the usual way, just in the standard way, takes a product, divides by the right action of S1, and this is a vector bundle. In fact, it's a line bundle, a complex line bundle. And the C-infinity section of this line bundle is just by standard isomorphism, the same thing as maps from the total space P to C, which transform or which are invariant with respect to S1, where S1 acts on P from the right as a principal action, and on C it acts from the right and from the left. It's in a Abelian group just by the representation. And since these are functions, it's easy to ask the question, does the space of vector field symmetries act on this or not? Does it preserve this invariance by S1? And it is a case. So we have an action of these symmetries on all sections of L. So in a certain sense, prequantization has a big advantage that the whole of the Poisson algebra acts on the prequantizing space, which is the sections of L. But we know this is not the end of the story. To go to geometric quantization, one adds extra data, one adds the metaplectic structure, and one adds the polarization. A metaplectic structure is just to have the notion of square integrable sections, and it's just a small topological condition to have the existence of metaplectic structures. And if you go to so-called MPC structures, then I think there's no obstruction to MPC structures, metaplectic complexified, and that's enough. But a polarization, this is really something, and you need existence, and you need eventually independence of the choice of polarization. So in certain cases like R2N, there you have beautiful theorems like isomorphism from Fock-Bachmann to functions which are defined only in terms of the base manifold Rn and so on. But in general, this is it's not obvious at all. Okay, but then another remark. As I understand from physicists, when they do quantization, they do not try to represent all functions on the quantizing space. In fact, they typically have a Hamiltonian, and they have some subalgebra of the functions, which might be functions which commute with H, but not always. It might also be that H is what is called a collective Hamiltonian, so it factorizes over the moment or co-moment of the subalgebra, but it does not necessarily commute with everything. And they have this Hamiltonian, they have this interesting, important Lie subalgebra, and they want to represent this on the quantizing space, on the linear quantizing space, so which is space of polarized square integrable sections of L. Okay, but today I will not come, unfortunately, to quantization in the two-plectic case. Okay, I think that's okay in time.
It's 5 minutes to post time of a break, but you of course can.
Yeah, I can start with the three forms. I do this differential topological thing, and after the pause, I come to the morphism. Okay. Or you want me to make the pause now? Then it will be a little bit long after the pause, maybe.
Okay, up to you. As you feel better.
Okay, then maybe I do this differential topological things for three forms, and then we come to morphisms. Okay. So the case of two forms was related to S1 because from a homotopical point of view, in the classical sense, this is not higher geometry, this is classical homotopy theory. The classifying space of the topological group S1 is the projective space of a Hilbert space, infinite dimensional separable complex Hilbert space, or if you want, it's a projective version of the unitaries on this Hilbert space. Homotopically is okay. And this is an Eilenberg-MacLane space KZ2, which means its cohomology is localized in H2. And this is a classifier also for in the sense of how to generate cohomology series by spectra. And if you go one level up, if you take the classifier now of the classifier, so Urs Schreiber loves to take B2. I'm not so good in homotopy theory and category, so don't write B2. I write B of PUH. This shifts my Eilenberg-MacLane, and we go to KZ3. Of course, you can write down models, but I'm not interested in models here. So this means that the third cohomology, the third integer cohomology, is geometrized not by principal S1 bundles, but by principal PUH bundles. Okay, so this is otherwise it's similar. Of course, there's a small hic, as we say in France, that PUH is a Banach-Lie group, but it's not finite dimensional. And then you have an analog of the first theorem, which says, I call it 1 prime. If you have a closed integral 3 form on a finite dimensional or sufficiently well-behaved infinite dimensional manifold, then there exists a smooth principal PUH bundle. I call it big pi. I don't know why I didn't call it small pi. Okay, big pi. From the total space I call Y because I need the letter P later on. Pi from Y to M. And I will explain what it means, but there is an associated lifting bundle gerbe, pi Y, which is in fact a principal bundle, but not over M, but over the second symmetric power of Y. And this has what is called a connective structure, which is similar to a connection in the S1 case, in the principal bundle case, but it's a bit more complicated, and whose 3 curvature is then related to the 3 form omega. And this implies that in analogy to the case we discussed, where we got the rationalized Chern class of the S1 bundle, here we get the rationalized Dix-Medour-D class. A PUH bundle has a class, a characteristic class, which is called Dix-Medour-D class, and it's a integral 3 class. And again, it's rationalized because I don't have torsion, I don't see torsion because I started with a form. This, in a sense,
Is it a two form?
omega is a 3 form.
No, theta, your connective structure.
Yes, theta is a 2 form.
And it's D is the omega, yeah?
I write it down in a second, okay? It's exactly what you say, up to some factors and pullbacks. Yeah. So what did I want to say? So it's again rationalized, and this is a pity in a certain sense, because if you have a integral 3 cohomology class on M, which is torsion, so n times the class 0, if you write it additively, then the associated PUH bundle or pH bundle, then the H in the pH or PUH bundle is finite dimensional. This would be nice because then you stay in a finite dimensional context. But since we work with forms, we are never in the torsion part, and we never have a finite dimensional H. So we are forced to go to infinite dimensional H. Okay, so I will try to explain the terms a little bit more. These things go back to Murray. He wrote a nice article which is called bundle gerbes, and then a second which is called Introduction to Bundle Gerbes. Okay. Okay, if you have a principal G bundle, then you can construct a map from the second power of the total space to G, because what is this symmetric second power? These are the couples y prime, which sit over the same point in the base manifold M. So they sit in the same fiber. The fiber is acted upon simply transitively by G. So if you take y prime and y in the same over the same point of M, there is an element of the group which from the right transports one point to the other. And this G is then unique. And you can say it depends only, well, it depends only on y and y prime. So you can call it chi of y prime. This gives a map from the second power to G. And now, if your G happens to have a central extension, for example, by S1, then you can use this map chi to pull it back to looking at the central extension as an S1 bundle over G, you pull it back and you get an S1 bundle over the second symmetric power of Y. So this is a principal S1 bundle. And this was coined by Murray and maybe other people, but I think it's Murray. It was coined a lifting bundle gerb. And later on, maybe only bundle gerb, but there are some subtleties in the notations. There's also gerb without E from Hitchin. Okay, this is, I think, the Czech version. So here in this case, PUH is our group G, and it has an obvious central extension, which is U of H. And then I can pull it back to Y2, and I have a S1 principal bundle over Y2. And this is the lifting bundle gerb one is interested here. And this can be reinterpreted as a very simple Lie groupoid. I think it's also called a central extension Lie groupoid. Because, of course, this symmetric power has two natural projections on Y, and this gives source and target. There's a small subtlety here. Pi 1 and pi 2 is the opposite of what you might think. It's not the projection of the case factor, it's the projection omitting the case factor, because you can generalize this to higher symmetric powers and you have a chain of projections where you always leave out one coordinates, let's say from the case symmetric power to the k minus first symmetric power. Okay, this gives again a principal bundle, And what Murray considered was a connective structure on this kind of gerbe. So it's a couple, A theta. First of all, A is simply a, well, not so simple, but it's a connection one form because it's a principal S1 bundle. So it's just a one form with values in I on this bundle. But you asked for more. You asked for compatibility with, well, you can formulate in language of gerbes or in language of groupoids. Here I formulate in language of groupoids, which I think for me it's easier. But it's a question of taste. This form is multiplicative, means that I look at this product, fibered product, P times P over M with respect to S and T. These are the elements of the total space of the groupoid which are composable. And I have the map M, the multiplication, the partial multiplication, which is here defined to P. And I have the two projections. Oh, there's a typo. I'm sorry. The second one should be a 2. Sorry. And the relation is that the pullback with respect to multiplication is the sum of the two forms. And then Murray proves, in fact, he proves it, I think, in 2 different ways in these 2 papers I quoted. Proves that if you have such a multiplicative connection form, first of all, it exists, such a multiplicative connection form. And second, there is a theta on Y with a property that, well, it's I valued, but that's not important. So that if you take D of A, this is a 2 form, I value 2 form on the total space, this equals the pullback, the difference of the pullback of the target and the source applied to theta. Okay, this is what is called a curving. I think this answered maybe the question of Thomas. He's not there. Okay.
Yes, sorry.
Okay. And furthermore, if you take D of theta, then D of theta again is a pullback, and it comes from the manifold, and this is called the 3 curvature. This is the analog of defining a Chern class or Chern classes in general by taking the curvature of a connection on the total space, and then, for example, in the linear case, taking traces, or in the line bundle case, it's not even necessary. So then it's a similar construction, only you end up on level 2 with the first Chern class, and higher Chern classes are even, they are forms with even grades, but otherwise it's a bit similar. So this is a 3 curvature, and this the cohomology class of this gives again the Dix-Menuidi class. Okay, so this is a construction of Murray. Okay, this is I think this is a natural point to stop. In the second part, I want then to speak about the analog of the KKS morphism. Okay, so shall we have questions there, or we just go to the pause, Kasia?
I think that we should maybe, if there is a question to this part, maybe it will be good to ask it now.
I have a trivial question. I guess the answer is yes, but I'll ask it anyway. So the manifold structure, since you have this UH, which
Yes.
is infinite-dimensional, the manifold structure you'll put on this PUH bundle
Yes.
is going to be Hilbert manifold?
UH is a Banach-Lie group, and PUH is a quotient by a compact S1 subgroup. It's still a Banach-Lie group.
Okay, so Banach manifold.
Yeah, it's not a Hilbert manifold. PUH is only a Banach-Lie group.
Okay, so Banach manifolds. Okay.
Yes, it's a but it's a smooth Banach manifold. You can realize it as a smooth Banach manifold. So from this point of view, it's okay, but it's not Hilbert, no.
Okay, thank you.
I think the big step in infinite dimension is not from Hilbert to Banach. From the point of view of differential calculus, the big step is then beyond Banach, because in the Banach category, essentially all theorems we use
Calculus works, yeah.
about vector fields and so on, they are all true in Banach situation. But in Frechet, we have to work very hard for this existence of flows, inverse mapping, and so on. All this gets very technical. So Banach and Hilbert, I think, is not a big difference from the point of view of differential calculus.
Yeah. Okay, thank you.
Any other questions at this point? It seems not. So it's 3:10 in Warsaw and 1 hour later in Romania. Therefore, we take, I propose 10 minutes break and we reconvene at 3:20 for the next part of the seminar.
Okay, nice. Thank you.
Sorry.
On the chat line, Thomas remarked I should recall some definitions. I will do it, but first I speak in general about Lie two-algebras, so I do it when we come back to our precise situation. It's true that it's one has to. It's not complicated. It's just that there are several objects one has to keep in mind. Okay, before I go to the analog of the prequantization morphism, which I will also recall, of Kostant and Souriau, I will speak a little bit about Lie two-algebras, because at least for now, the best we have in multi-symplectic geometries, instead of a honest Poisson algebra of observables, is we have Lie n algebras for an n-plectic manifolds, which nice and sexy and everything, but they don't have these good properties one would want to have. But for the moment, one has to live with it. But I think it will not be the end of the analysis. I think it's in a certain sense it's too meager to have the right algebra of observables for a field theory to formulate it in these terms. We will see this in a second, more detail. Okay, let's recall the definition of a Lie two-algebra. So a Lie two-algebra is a special case, a very simple special case of a Lie infinity algebra. So from this point of view, it's rather simple. That's okay, because if I want to write down all arrows and so on, one can do it still. And there are not so many terms. It's sort of understandable. Okay. So what is in general a Lie two-algebra? There are several points of views. I take a point of view which is strictly non-categorical. I take a two-term complex of vector spaces, which is a stupid expression for saying I have two vector spaces and a linear map between them. A Lie two-algebra on this complex is a collection of three multilinear maps, which have a degree, because the terms, they come with a degree. And so we have L1, which is just defining this complex. Then we have L2, which is a map, now you see it, 2 minus k is a map of degree 0. So if you plug in 2 elements of L0, you still get an element of L0. But if you plug in 2 elements of L minus 1, you get an element of L minus 2, which is not there. And if you plug in a mix, you get an element of L minus 1. Then you have an L3, which for degree reasons can only go from the third exterior power of L0 to L minus 1. So there are a lot of different conventions in this business. You can take also symmetric powers and so on, but okay, I take this convention. And then there are compatibilities between these structures, which sort of generalizes Lie algebra, differential Lie algebras, or maybe the best thing you can easily imagine is a differential graded Lie algebra. I think everybody can write down in a sort of automatic way the right relation for a differential graded Lie algebra because it's very natural. And these are generalization of this. I wrote them down, but I don't want to discuss them. It's not so many equations, but you see it's already quite a bit. And you can imagine if I go to Lie 3, then number of equations goes really up. Okay, so it's a Lie 2 algebra. I don't want to discuss in detail these equations. I want to discuss an easy example of Lie 2 algebras. In fact, there are two extremes of Lie 2 algebras. One is L1 is 0, and one is L3 is 0. L1 equals 0 is called skeletal, and L3 equals 0. This also has a term, but I forgot it. Strict, maybe. Yeah, strict. And this is the same thing as a Lie algebra crossed module. So what is a Lie algebra crossed module? This is given by two Lie algebras, H and G. And the second Lie algebra, G, acts on the first Lie algebra. And we assume it acts not only linearly, it acts by derivations. And we also have a morphism from H to G. And we ask for compatibilities, which in a certain sense, if you try to write down compatibilities, from an algebraic point of view, these are the only formulas you can write down. Yeah. So, for example, if you want to write down something with two elements V and W in H, okay, you have a commutator. And how can you get it with these H and eta and theta? Okay, you take eta of V, you land in G, and then you can act again by theta because you are in G. So you have theta of eta of V with W, and this should be the commutator. So that's already an interesting thing because I will reformulate it without the bracket on H. And you might think you lost information, but this formula shows that the commutator of H is fixed by the other data. And then the only thing to work here in a mixed way, so you have theta xw, you have a mixed term, you land in H, and you can, with eta, you can go back to G, and this you can formulate as a commutator in G. You take the X, which is already in G, and then you transport W with eta to G and take this commutator. So Lie algebra crossed modules exist in many categories. Essentially, most well-known is Lie algebras and groups or Lie groups. Lie groups, let's say. And the interesting remark I already made is that a Lie algebra crossed module is essentially the same thing as a strict Lie2 algebra. So this is a Lie2 algebra such that the third bracket is 0, the L3. And so if you know what is a Lie infinity algebra or Lie2 algebra, the L3 is important to correct the absence of the Jacobi identity. The traditional Jacobi identity is given in terms of L2, and in certain sense it's L2 composed with L2, and this should be in a Lie infinity algebra L1 composed with L3. Now that's the idea. So that's a notation of Stashev to compactify all these things. So if L3 is not there, then it means that you have Jacobi. Okay, so how do you go from the Lie algebra cross module to a Lie2 algebra? Well, you plug L0 as G, L-1 as H, and L1 is this map eta. That's the only way you can do it. And then you have to look at the higher brackets, L2, okay, on G, you take the commutator. For the mixed L2, you take the action, and if you are with both factors in H, you are in L-1, then the L2 is automatically 0 by degrees reasons. That doesn't mean that the Lie bracket of H disappears. It's just not the L2. The Lie bracket of H can be got back by the formula A1, because you have the theta, the mixed one, and you have the eta. So you get back from the Lie2 algebra to the cross module, but it's not L2 which gives it to you, because L2 on the first term is 0. And L3 is 0 because it should be a strict Lie2 algebra. And later on, I need an important example of a crossed module related to groupoids. So let's try it. I will try to explain it. It's again some notation. So in general, I will apply it later on to the groupoid P goes to Y, and I will recall exactly what everything was. And here I take a general groupoid. So I take a groupoid G1 with 2 arrows to G0, source and target. And I have a vector bundle over the base G0, which is called the algebroid, Lie algebroid. I write it Lie G1. This, you have to decide how you do it. I take the kernel of the differential of the source map. So this defines S and T are submersions. So this is a sub-bundle of the tangent bundle of G1. And I restrict this bundle to the unit section. Okay, a groupoid has not only one unit, it has one unit over each point of G0. So you can take the unit section, and we restrict this vector bundle kernel S star on the image of the unit section, or you pull it back with epsilon. With the unit section, you pull it back to G0, so you can see it as a vector bundle over G0. Okay, S and T are source map, epsilon the unit map, I is the inverse, and then you have the right and left multiplication by a fixed element. Of course, it doesn't act everywhere. It acts only on the point so that you are composable from the right or from the left. You can define right and left invariant vector fields on the total space. This is as in the group case, but of course, again, one has to take a little bit care. So I take a section A of the of the Lie algebroid, associated Lie algebroid, and then I take, well, I should write even an epsilon here. I suppress the epsilon. I take an element G and I want to understand what is the right invariant vector field. No, this is the left invariant vector field. The left invariant vector field no, this is the right invariant vector. The right invariant vector field associated to A. So I go to the target point, then I apply A, and then I shift it around by right multiplication. In the other direction, I intertwine an inverse. This makes me get a plus here. Other people have a minus here. And then the sum of the left and the right invariant vector field is what is called a multiplicative vector field. And I recall the definition. So a multiplicative vector field on a groupoid is a couple of two vector fields, one on the total space, one on the base space, and this couple Cx defines a Lie groupoid morphism. Okay? Because this, on the right-hand side, we have again a Lie groupoid. We have the projection S and T are replaced by S star and T star. The Lie algebra of these multiplicative vector fields is denoted multiplicative vector fields. Well, one has to check that the commutator of two of these vector fields has the same property. And I calculate an example inside this example. So if the base is just a point, then the groupoid is a group, Lie group, with Lie algebra. And the tangent bundle is, you can trivialize it with the left invariant vector fields. So you have the vector fields or the neutral, the tangent space is a neutral point, semi-direct with G, and G acts on the Lie algebra via the adjoint representation. And then what is a section of the Lie algebroid? G0 is just a point. Lie G1 then is just the Lie algebra. And so the sections are again just the Lie algebra. And this eta left plus right invariant vector field with an inverse inside. This gives a minus here. So this is, I take G, the left invariant vector field. So I have the A here and the right. This is just in G is in the trivialization, it's always A. And on the other side, if I trivialize by left invariant vector field, the right invariant vector field associate to an element of the Lie algebra in the point G is written as adjoint action of G on A. So, and the minus is because of my inverse, and G is just the point G. So this is just the multiplicative vector field in the group case. So now we go back to the example. Okay, there's again a typo because it's not the anchor of Lie P, it's the anchor of Lie G1 in general. I will correct this. G1. So we had this eta of A, which is just the sum of the left and the right invariant vector field. And I said a multiplicative vector field is a couple. It's a vector field on G0 and on G1. So this is the upper part. This is the eta and the psi. And the lower part, well, the Lie algebroid comes with a vector bundle morphism to the vector fields of the base, G0. This map is called the anchor. And so the couple psi and x is eta of A, which is the sum of the left and the right invariant vector field associated, or the difference of these left and right invariant vector fields. And the second part of the couple is the anchor, which is a vector field on G0. Okay, so this is the example. And I continue this example. There's a natural crossed module. So I have these multiplicative vector fields, and they act on Lie algebroid sections in the following way. I take the right invariant vector field associated to A. I have the multiplicative vector field. I can take the commutator in the sense of vector fields, and I have to check that this is still a right invariant vector field, so it's associated to a section of the algebroid, which is the case, and thus I have an action of the multiplicative vector fields on the algebroid, on the sections of the algebroids, and thus in the end I have a crossed module, and I have written it down here. So the cross module here, you have the section of the algebroid, you have the eta, which we described in the beginning, giving a multiplicative vector field. The multiplicative vector fields act on this, which is also a Lie algebra, because the algebroid is a Lie algebra, the sections are Lie algebra. And then one has to check all together, it gives a crossed module. And this is a natural crossed module associated to this groupoid. And thus one can construct a strictly two-algebra by it, because of the construction above, that a crossed module gives a strictly two-algebra. I don't know who created this construction. I think Ping Xu and Mackenzie, they defined multiplicative vector fields many years ago. Well, they were not the first, but I'm not good in the history. And this construction, several people were involved. I remember that Camille was maybe involved, but I don't know who was exactly involved. I'm not an expert in the history of this subject. Okay, so we have this natural Lie2 algebra constructed of the Lie algebroid and the multiplicative vector fields. And what I also want to say is what is a morphism of Lie2 algebras? I write it down in arrows. It's a bit of a pain, but then there's a diagram which helps a lot. So I take two Lie2 algebras. Then a morphism is given, first of all, by a morphism of complexes. This is a phi 1, which has degree 0. And then I have a correcting term, which I write in a diagonal way. And they have to have a lot of compatibilities, which I do not want to discuss, but it's natural. But the easy way to remember is the following. I have the two Lie2 algebras written as very short complexes. Then I have phi 1, which is a morphism of complexes. So the outer square is commutative. And then I have this strange arrow in the middle, which is not an arrow from L0 to L prime minus 1, but from the second exterior power of L0 to L prime. And this is sort of the correction that the algebraic structure should be corrected with. I think if you look at it from an abstract point of view, from Lie infinity and so on, then this is just, well, Lie infinity, you have abstract ways to see it as with co-derivations, and you have morphisms which preserve co-derivations and so on. And then you dualize and you get a lot of identities on the other side. And if you cut down to short complexes like Lie 2, then this is what will survive in the end. So in a certain sense, probably it's more natural to look at Lie infinity than to look at this. So it is, in fact, a Lie infinity morphism between two Lie infinity algebras, which are very small. Okay, this is a Lie 2 algebra morphism. And in the world of Lie 2 algebras or Lie infinity algebras, one does not really look, or maybe too optimistic to look for isomorphisms, as in the world of Lie algebras. And I remember that the KKS prequantization morphism was an isomorphism of Lie algebras. Here, the right notion is quasi-isomorphism. So it means it is a morphism in the world of Lie 2 algebras, but it's not an isomorphism from the point of view of vector spaces or complexes. It's an isomorphism once one goes to cohomology. Yeah, this is a quasi-isomorphism between two complexes. It's a morphism of two complexes. There might be infinite. You have degree 0 map, and all these squares commute. So that means essentially that D and D prime are compatible of the two complexes. And you don't ask for isomorphy. You ask for isomorphy once you go to cohomology, because a morphism between complexes induces a morphism between the cohomologies, and you ask for isomorphy on cohomology level, on cohomological level. That's a quasi-isomorphism.
Phi 1?
Yeah?
Is it a condition just on phi 1, or does it somehow take into account the phi 2 as well?
Pi 1?
Phi. So the morphisms on homology are induced by the vertical arrows phi 1. Is that what you mean?
Yes. It's only phi 1. Yeah. Phi 2 is not important for this notion of quasi-isomorphism, but phi 2 is needed, possibly needed, because the whole should be a morphism of Lie 2 algebras. And it's possible that without phi 2, you don't get it. For example, if you have an arbitrary Lie 2 algebra, you can get rid of L3. Yeah? Or you can also get rid of L1. And you get quasi-isomorphic Lie 2 algebras with L1 equals 0 or L3 equals 0, but you cannot get them only with phi 1. You have to correct the errors with phi 2. So you have quasi-isomorphisms to either skeletal or strict Lie 2 algebras, but you have to pay a price. You need the phi 2 for these maps to be also morphisms of Lie 2 algebras. Okay, now I come to the morphisms. So I have cut it in two chapters, flabby and rigid prequantization, and you will see in a second why. Okay, the first thing is what are the right observables in the two-plectic case? So what we use is the Baez-Rogers observable algebra, which is for an n-plectic manifold an Lie n algebra. So here in the two-plectic case, it's very easy. It's just the functions and the one forms but it's only the one forms which we call Hamiltonian. So it's a one form such that contraction that D of alpha is realized by contraction of a vector field with omega. So alpha is a one form, D alpha is a two form, omega is a three form, iota x alpha of omega is again a two form. So this makes sense to say that these are typically not all one forms, it's a subset, okay? It's a vector space, but it's a subset. And what are the algebraic operations? So L1 is just df. Then it's stupid because d of df is 0. So these one forms, they have associated the zero field. L1 of a one form is 0. And then you have L2 and L3, which are constructed in the same way. You have Hamiltonian form, so you have vector fields associated. You contract them in the form. So if you have 2, you contract in the 3 form. You have a 1 form left. If you have 3, you contract the 3 inside omega. You get a function left. So this is okay with the degrees. And then in principle, you have mixed terms for L2, but they are 0. So if you mix a function and a form, it's 0. If you take two function, it's 0. So it's an extremely easy Lie-two algebra. This observable.
So if you have a 3 form, so the 3 form was closed, right? Omega was
yes,
closed.
Yes. It's a closed 3 form.
You have a 3 form, and you consider those Hamiltonian sections. You can consider the Courant brackets on Hitchings' generalized tangent bundle over M. The Courant bracket being twisted by omega, a la Chavera and
Yeah, that's the same. I think it's the same. Yeah.
Well, that's okay.
I think.
What's the same? It's the same algebraic structure. What do you mean? The same.
This is a Lie-two algebra here. I think it's written down, for example, in detail in the PhD thesis of Antonio Miti with Marco Zambon.
Yeah, but what's the relation to this? Because the point is that this Courant bracket closes on such Hamiltonian sections. That's easy to check. And the question is, what's the relation of this Courant bracket of such Hamiltonian, if any, to this Lie-two algebra that you described? Is there any clear cut?
I think essentially it's the same data. In that case.
Thanks.
But you should check the thesis of Miti, M-I-T-I. There are papers on the web, and probably even his thesis is on the web. He describes that also in higher cases, 3- and 4-plectic. But I think beyond 4-plectic, it's getting really messy, and he sort of gives up in a certain sense in the thesis. And then there's a paper of Miti and Zambon where they organize the algebra a little bit better, and you should look at the paper, at least in the archive. It's easy to find.
Thank you.
So there's a close relation to that. Okay, from my point of view, what is not good about this is that this is not really a Poisson algebra because you do not have this pointwise multiplication, not even in a graded sense or something. For example, one weird thing is that if you take a Hamiltonian one form and you multiply by a function, it's not necessarily a Hamiltonian one form. So it's not a C infinity M module. So it's from a point of view of a classical Poisson algebra, it's really not good. So I think there's work to be done. Okay, so the first analog of theorem 2, I remember theorem 2 was about the morphisms, that the Poisson algebra of the base manifold M is isomorphic to the symmetries of P and A. Okay, let's start with a two-plectic manifold with integral omega. And a global geometric prequantization is this structure with Y. So Y is a PUH bundle over M, which I called big pi, the map. And over Y2, there is a natural S1 bundle over the second symmetric power of Y, and I reinterpret it as a what is called, I think, S1 extension gerbe or something, or line bundle, well, it's a bundle gerbe, which I can reinterpret as a very simple groupoid over Y. And I fix the connective structure, which is essentially connection on P over Y2, but with a one form which is multiplicative, and then you have this theta, which is a curving, and you have this free curvature. Then lead to algebra. Yeah.
May I have a follow-up question? So if you look at this Courant algebroid twisted by the three form, then it may happen that, for example, some vector fields coming from a geometric action of a group on M close to a Lie algebroid, and then the obstruction to their closing to a Lie algebroid, actually an action Lie algebroid, within this Courant algebroid, so a Dirac structure in other words, is the first sort of non-topological obstruction to gauging the symmetries, this geometric action of the group on the base of the gerbe, lifting it to the gerbe as an equivariant structure on it. Do you have a similar statement, a parallel statement?
I think so. I think so. I honestly, I don't know very well the language you use, but you will see I have a second version of the theorem, which is not flabby, and there things you quote will show up. Okay?
Okay, very good.
Okay, so we have a Lie two-algebra morphism from this Baez-Rogers algebra to this Lie two-algebra we discussed coming from this crossed module we discussed beforehand. And I wrote the arrows, but I do not have the time, and maybe one has to read it in detail to understand. So the first part, okay, phi 1, this is a degree 0 part of the complexes. The function goes essentially to function time Euler field. The form, this is a little bit complicated. I will explain it in a second. You take the form, you take the field, you lift the field, you double the field, you lift it again. So I'm not really that happy about the formula. And the correction term comes again with a big omega. This comes from the bundle Y over M is a PUH bundle. It's a smooth principal Banach-Lie group bundle, and you have connections, and you choose a connection which gives the curvature omega. And I'm again not. I don't know what. I don't know better for the moment. Okay, so here it's written. ZH, the H there is a horizontal lift of a vector field on M with respect to an auxiliary principal connection. Here, this is a doubling of a field. So I take alpha, I take the associated field, I lift it, I double it, and I lift it again to the principal bundle. Okay, so this, but maybe I don't want to go into the formula so much. This is a correction term here. And I want to remind that in this situation, P is a very simple groupoid. And in fact, you understand all the multiplicative vector fields here. They are of the form, you take a vector field X on Y, you double it, and you lift it. and you take a function on y, and you take the delta of the pullbacks times this S1 vector fields. So it's a little bit similar, or maybe even very similar, to the one-plectic case, where here you have xf tilde, and here you have q upper star of a functions time z. So it is rather similar. And okay, non-uniqueness says maybe I should. So I wrote down the formula in the one-plectic case, which looks like this. So this is rather similar. So the multiplicative vector fields, they are rather similar. But in the one-plectic case, these are all the symmetries of the one form A. They look all like this. Yeah. And now the question is, in which sense is this true in the two-plectic case? And there's a phenomena coming up, which you might call a gauge. You will tell us in a second. So we try to repair, because now, for the moment, it's a little bit flabby, because this morphism here, these are not the symmetries, not the Lie two-algebra of symmetries. These are not the symmetries. And the phi is not an isomorphism, okay? And this we want to repair in the best possible way in the world of Lie two-algebras. So now I go to the rigid version. So first of all, I remind you what are the objects. Y is a PUH bundle over M. I did not rewrite it here. I should maybe add it. I will rectify the slides and send them to Cassias, or you can send me an email, but I will make small corrections. Okay, so you have this principal S1 bundle, you have the associated Lie groupoid interpretation, you have the multiplicative form, and you have the curving theta. So now you want to define what is the symmetry or an infinitesimal symmetry of A, or of A and theta. So you take a multiplicative vector field, because you have the A which lives upstairs, and you have the theta which lives downstairs on Y. And then you have so it's natural that a symmetry is a couple of vector fields, one upstairs and one downstairs. So you take a multiplicative vector field, and your freedom is this B. So maybe this B in a certain sense fits with your idea of a gauging. We say that a triple multiplicative vector field plus a one form is a weak symmetry. So it's not a symmetry, it's a weak symmetry if you derive upstairs the form A with respect to the field, vector field psi, and it's not zero, it's T star minus S star of B, because it's a one form on B. And downstairs on Y, you derive the one form theta, and again, it's not zero, it's D of B. So it's a weak symmetry, because a strong symmetry, for a strong symmetry, you would expect that you find 2 times 0. But here you don't find 0, you find a correction term B. Okay? And this we call a weak symmetry. And okay, I put them together. Does this fit with your ideas of a gauge?
No, it's hard to say. I mean, my idea of gauge was lifting the vector fields generating a group of fundamental vector fields from the base of the gerbe. So I cannot really tell.
Okay.
Hard to say.
Let's continue. Okay, in the notation, we will suppress A and theta. It's fixed. B is not unique. This is clear. You make an easy calculation. You take a closed one form on M, then it disappears in the formulas. And then there's an important observation which relates to multi-symplectic geometry. If you have a multiplicative vector field, then there exists a B so that it completes to a weak symmetry if and only if the projection of X to the base. X is always a projectable vector field. You can always project it to M, but you need that this projection P star of X is Hamiltonian on M. That means there's a one form such that you have this formula, as we discussed already, this Hamiltonian vector one forms. And since we know how a multiplicative vector field looks like, I wrote it here again, then we can write down the B. Yeah, if it's a weak symmetry, it's an explicit formula, but I don't want to discuss it now. But it's again the alpha going in the formula. Now I will write down a formula which I'm not very happy about it, but I will write down it was a splitting. In this special case where this Lie algebroid comes from a sort of a S1 Lie groupoid, you can split the algebroid in vertical vector fields plus the infinity function just by using the connection A. And so vertical vector field is just the kernel of pi star along the fibers of the PUH bundle over M. And a function corresponds to, again, to the function times the Euler field. And then you can write down the formula. So this, maybe I do not want to exaggerate with this formula. So this formula we have seen, that this is a form. Okay, I write down, maybe it's, I don't go to each formula now. So you have, in this splitting, you can rewrite the action. So you can rewrite the cross module. And then you get a complex of weak infinital symmetries. The section of the Lie algebroid and the weak symmetries form together again a crossed module. Okay, so this refines the situation. And now we have a close analog of theorem 1, the rigid version of 2. So again, I have the Baez-Rogers algebra, and here I could also write sections of the Lie algebroid. And these are the infinital symmetries. And now I have, again, a morphism. So I take less elements here in a certain sense because I want symmetries, but I have to correct by the one forms. And here I take again the sections of the Lie algebroid. And now I have a morphism of Lie two-algebras, which is a quasi-isomorphism. So in a certain sense, it's the best I can hope for. It's not an isomorphism of Lie one algebras, of classical Lie algebras, but it's a quasi-isomorphism of Lie two algebras. And I explicitly give all the formulas. Maybe I don't want to discuss too much the formulas. I just want to remember that the theorem 2 was an isomorphism of Lie algebras in the one-plectic case. And now I get a quasi-isomorphism of Lie two algebras, but it's onto the weak symmetries. Okay, I think I want to stop here. I just give the references. There is a parallel work which is a little bit differently formulated of Krebsky and Warhan, and it doesn't work. They don't speak of geometric prequantization, but they do similar things in a very related language, a little bit different. This is a classical Murray paper. This is one of the papers which describes the first part, the motivation. This is this paper I discussed today. And this is a paper which discusses also the motivation. So, okay, I will stop there. I don't know if Kasia is still there. Maybe I overdid her patience.
Yes, I'm still here. I mean, the camera doesn't point at me. Maybe it will. Oh, it's not at me. I'm still here.
Okay.
And since we arrived to the end of your talk, I asked the question if there are questions. If you could, Tilmann, if you could look at the chat. Probably the speaker usually doesn't notice the chat, but at the,
I've seen it a second ago. Well, there's a question of Thomas. I think I answered. There's a question of Julian Alzate. If these weak symmetries are analogous to symmetries up to a total derivative in classical mechanics. I think the answer is yes. I didn't thought about it in this way, but it's a nice idea to think about it in this way, because the whole constructions in multi-symplectic geometry is in a certain sense always the algebra closes up to a total derivative and the symmetries formally algebra up to a total derivative and so on. So it's, if you read the old books on classical field theory, then you find always these kind of terms which are given in terms of integrals, in terms of Lagrangian variational calculus. But here they are without, well, the variational calculus is hidden in a certain sense. It's somewhere. If you look at my paper with Maxim Wagner, you see it explicitly. So I think the answer is yes, but one should make it more precise. Then there is a second of Kalin Lazaroyo. Can you comment on relation to deformation quantization approach? Yes, it's a good question, but I don't know. Is there something like deformation prequantization? I mean, in a certain sense, you do not you try to deform everything. So and everything, and you don't represent it on a space. So probably there is a relation, because in a certain sense, prequantization compares more easily, I think, to deformation quantization than geometric quantization after polarization. So I think in principle it should be true. I know that Giuseppe Dito and maybe other people tried to do deformation quantization in infinite dimensions. Also there's a question how it relates. A good example, I think the only example which is not exactly in this language, but which is a little bit similar, is a thesis with Frédéric Hélan in the case of the Klein-Gordon equation. They tried to first they formulated in a multi-symplectic way, which is very easy, and then they tried to sort of rewrite it at least perturbatively in quantum field theory, and I don't remember the name. If you send me an email, I will find the paper. The student was from Madagascar, so he has a typical Malgache name, but I don't know it by heart.
One question I have about this is, I guess you need the space of fields to be a Banach manifold if you want to apply your approach, right? A smooth Banach manifold, because you somehow assume that the base manifold and the base bundle were ordinary differential geometric manifolds. And I guess it's pretty trivial.
I'm not sure because
Gordon, if you put it on non-compact manifold, right? It's quite difficult to construct a space of fields that's physically relevant, and that's actually a Banach manifold. It's usually you need this complex condition or something. You end up with manifolds.
If I just look at the construction, I'm not sure. Probably you're right in the end, but as it is presented, at some point I look at C infinite function on the total space of Y. Y is a Banach manifold, okay? So if you look at all C infinity manifolds on a Banach manifold, I don't think it's a Banach space.
Y was fibered over an ordinary manifold. And what I'm saying is that in a quantum field theory, there's not going to be a finite dimensional manifold, right? I mean, there's going to be some kind of manifold of fields.
Yes, of course. In a certain sense, it's
in what sense it's a manifold?
The construction doesn't stay finite dimensional. That's clear because once you take the PUH bundle over the finite dimensional base manifold M, even if M is compact, you take a PUH bundle, it's not compact anymore and it's not finite dimensional anymore. It's just a Banach manifold. So, of course, one would like to make an approximation by finite dimensional PUH bundles. But the problem is that finite dimensional PUH bundles have vanishing rationalized Dix-Medourdi classes because they are torsion. Right. And so I don't know how to approximate. That was the first idea, of course, to approximate this by a sequence of finite dimensional Hilbert spaces, and hoping that the whole information you need is concentrated in finite dimension, like in homotopy theory, it's very often the case. But in this case, it doesn't work because if you cut H to a finite dimensional space, then a PUH bundle or a pH bundle, projective Hilbert space bundle with this fiber, has a torsion Dix-Medourdi class. If you rationalize, your 3 form you get is 0. So there's some problem which up to now I cannot solve. That's sort of disappointing in a certain sense if you have the philosophy that multi-symplectic geometry helps you to stay finite dimensional all the time. So.
Okay, thank you.
Okay, so are there any more questions? If not, I propose that we first thank the speaker. And then I would like to thank you all for being here today. And since we are coming to Easter, and this year it is both Orthodox Easter and Catholic Easter at the same time, so I can wish you all a happy Easter.
Happy Easter.
To those who celebrate and to those who just rest at this period. Have a nice time. We meet again in a week on Wednesday after Easter. Rafał Suszek, who had to vanish now because the student was waiting for him, will teach us about principaloid bundles, which will be definitely very complicated and esoteric subject. So you are all welcome.
Okay, thank you very much.
Thank you.